Hi, and welcome to Quantum Mechanics Revision 6, the Photoelectric Effect! Now, I know we've done this to death, I know we've done this so many times, but there has never been an A-level physics paper without a photoelectric effect question, and frequently it's 10 marks, 6-mark essay plus some other bits and bobs. So, if you know the photoelectric effect, you're guaranteed some marks, isn't that great? Just like that. So I'm going to go through it one more time, nice and slowly, just to make sure we know all the little bits and we've got it exactly right. I'm actually going to start by the two things they always want you to know. I'm just going to put those in your mind now, and then going to return to them at the end. So the two questions they ask over and over and over again are, why do some colours of light emit electrons and others don't? And also, why is the fact that electrons are emitted spontaneously important? So they're the two things, colours of light and instantaneous emission. So we'll get back to those, but just remember that's what we're driving towards. So, what is the photoelectric effect? Here we've got our energy well around an atom. So remember, these are places an electron could be while orbiting an atom, with anything over here being they've left the nucleus and they're flying around doing their own thing. And this is how much energy we need to put in to get them to escape from different points. So if they're quite a long way from the atom, you only need to put in 0.8 electron volts to make them escape. If they're really close to the atom, you need 10 times as much, 8 electron volts. Okay. So, how can we make them jump out? Well, as we've talked before, there are two ways we could do it, which is we could heat up these electrons or pass a current through them and that would give them energy. But there's a third thing we can do, which is if a photon comes in and smacks into one of these electrons, if it's got enough energy, the electron can take all that energy and fly all the way out. Now what's interesting is, because we're dealing with quantum phenomena, you have to take all the energy or none of it. You can't take a bit of it and leave a less energetic photon. All of the energy from that photon has to come in. So you can think about it coming in lumps. There's a lump of energy, you get all of it, or you get none of it. So let us consider what would happen if we were to bombard this particular atom with energy of 0.4 electron volt photons. So lots and lots of 0.4 electron volt photons start smacking into this. Think for a moment, will that do anything? The answer is no. Because 0.4 electron volts isn't enough for any of these jumps to occur. If you give an electron here 0.4 eV, that's not enough for it to get up to the next one. And remember, it can only exist here or here, so it can't accept the photon. It won't do anything with the photon. The photon will just rock up and go, and then just continue on its way. Similarly, we need a full 0.8 to get out of here. Now, let's also, on the other hand, consider what would happen if we hit this with something of 2 electron volts. Well, actually, 3 different things could happen. Firstly, the 4 one could go, that's exactly enough for me to jump up to the 2. So I'll take that and nip up here. The 2 one could go, that's exactly enough for me to nip up to the top here. And then I'll just escape and I'll have no extra energy. But interestingly, the 0.8 one can take it too. It can go, I'll take all that energy, I'll use 0.8 of it to get to here, and I'll still have 1.2 electron volts of energy left. So that would be kinetic energy for me to fly away, fly straight away and get out of this atom. I've got enough energy not only to escape, but to keep going and really make a run for it, nice and quickly. So if light is hitting this, and all the photons have 0.4 electron volts, nothing will happen. Never mind how much light we shine on this metal at 0.4 electron volts per photon, nothing happens. However, at 2 electron volts per photon, electrons will have enough energy to leave the energy well and start coming out the back of the metal, and we can measure them. Okay, so here's your very standard question. You've got a bit of metal, you shine absolutely loads of red light on it, loads and loads and loads and loads and loads, and nothing happens, nothing at all. But you get another piece of metal, and you shine just a tiny bit of blue light on it, and then electrons start flying off. Whee! So despite the fact there's way more energy of light hitting this bit of metal, electrons are coming off this one, but not this one. Why? Pause the video, you should be able to answer this. The answer is that none of the photons in the red light have enough energy to take the electrons out of the well. So you can shine all the red light on the metal you want, all of it, and nothing will ever happen because it's coming in lumps, and you can't get two lumps at once. You've either got to accept each individual lump. The energy is quantized at a quantum level. However, we shine a very small amount of blue light, and each photon on this has enough energy to maybe get the 0.8s out, yeah? And then those electrons will start to be released and we can pick them up. So that is our colours of light question answered. Now we've got instantaneous emission. Classical physics, if you don't understand about photons and quantum and quantized energy and all that kind of stuff, would tell you if you just shone enough red light on the metal, the energy overall would build up, each electron could store the energy over time, get enough, and then fly off. It actually says similar things should happen with the blue. You shouldn't get electrons straight away. Instead, each electron should get a bit of energy, get a bit more, and then they'll all start to fly off. But because it comes in lumps, the very first photon will have enough energy to ping off an electron, and it'll transfer all of that energy in an infinitely small amount of time. So the moment you turn on the light, you'll start to get electrons, which is not what classical physics would tell you, but the quantum physics explains it perfectly. So these are the two things they're always asking. Colours of light is because of the different energy in each photon in the two different colours. And the instantaneous emission is because the energy in one photon is transferred to one electron straight away and then that electron's off. Both of these are not what you'd expect from classical physics, but just by looking at the quantum mechanics, we can easily explain both. There's a question underneath. I'll see you later in the week.